Time to start paying pretty close attention to what we got going on. So if you were not super focused in on the warm-up, make sure you tune in now. Put your phones away if you got them out. So here we go. What are all the real cube roots of x, not x, but of 125? So it says, first of all, let's go ahead and set this up a little bit. An nth root of a number c is x such that x to the n power equals c. Basically what we're saying is, if you have a number and you raise it to an exponent, it's equal to the result. So basically what we're saying here is that c is 125. Something raised to some power is equal to 125. And we're looking for the cube root. So what we're saying is something raised to the power of 3 equals 125. That's what this means. An nth root can be represented using a radical symbol by x equal to the nth root of c. So basically what's happening is you can write an exponent and a root as inverse operations of each other. It'd be like multiplying versus dividing. Exponents and roots are inverse operations like multiplying and dividing, or adding and subtracting. So what we're going to be doing here is we're going to say, all right, what can we take to the power of 3, x to the third power equals 125, and we're trying to solve for x. That's what we're looking at here. Now, what it's telling you over here is it's showing you a graph, and the graph is just a visual approach here. We're not going to be using graphs very often, but if we were going to be actually graphing this, we would have to set this equal to 0, and so we would get x cubed minus 125 equals 0. So if we just go over this way for a second, we get x cubed minus 125 equals 0. And that's the function over here. This is the function y equals x cubed minus 125. And so what's going on over here is when you solve for x in an exponential equation, or if you're using exponents and you're taking the root to undo it, when you solve for that x value, essentially what you're doing is you're figuring out a 0 on a graph. And we just got done with an entire unit in polynomials. We talked about finding zeros and all that kind of stuff. So basically this is the same as that when you solve for x. So what do you notice about where this graph crosses the x-axis over here? Where does this graph cross the x-axis? At 5, okay. So let's think about this for a second. If we were to solve this, basically what we would be doing is we would be saying x is equal to the value of c, which is 125, cube rooted. So we're asking ourselves, all right, x is equal to the cube root of 125. What number multiplied by itself 3 times equals 125? 5. So x equals 5, which is exactly what the 0 on this function over here is. That would be the real root. And the reason why I'm specifying a real root here is because the answer is 5, by the way. The reason why I'm specifying a real root is because there are complex roots of this. Actually, let's discuss that for a second. There's a little thing off to the side here. It says, recall that third-degree polynomial functions have 3 solutions. Right now, we only see 1, because there's only 1 real solution. But there are 3 solutions. Hence, one solution is real, and the other 2 are complex, meaning they have the imaginary unit. How could you find the complex solutions? Any thoughts about that? I'm going to use this real quick. Again, we're not going to be doing much, we're actually not going to be doing anything with this kind of thing today, but I do want to mention a couple things as we're going through this. Because first of all, today, we're only dealing with real solutions. We don't need to worry about complex or imaginary solutions. However, the knowledge that something to the third power has 3 solutions, even though there's only 1 real solution, that's a good thing to know, even if we don't use it. So if we have x cubed minus 125, go ahead and write that up at the top of your paper here. You remember from like not even a week ago, something that looked like that. This is a difference of cubes, which is equal to a minus b times a squared plus ab plus b squared. So if we were to factor this, we would get x minus 5 times x squared plus 5x plus 25. And this one right here, if we set that equal to 0 and we solve for x, we get 5, which is the real solution here. However, if we were to solve for this one here, we'd have to use the quadratic formula. And when you use the quadratic formula with this, you end up with negative square roots and complex numbers. We're not going to do that here, but I just wanted to show you that there are 3 answers here. 2 of them come from over here, and they are complex because they both have I. The real solution comes from this one when you set it equal to 0, it's 5. We are only dealing with the real stuff today, so we don't need to worry about this right now, which is kind of nice. I just wanted to relate that just to show you. All right, so for part B, what are the real fourth roots of 16? So basically what we're doing here is we're saying, all right, if we have x to the 4th power equals 16, and we set that equal to 0, and we solve for x, so x to the 4th minus 16 equals 0. There will be a quicker way to do this, by the way. I just want to show you where we're getting our answers. So if we were to basically graph this and figure out where it crosses the x-axis, there would be 4 solutions. Maybe there's 4 places where it crosses the x-axis, maybe not, but let's find out. This right here is a difference of squares. So this is what we saw in the last unit. A squared minus b squared is equal to a plus b times a minus b. So we can factor this, and it turns into x squared plus 4 times x squared minus 4. Now this one here, if we were to set that equal to 0 and solve for x, those would be complex solutions. Because if you square root a negative, you don't get a real number, you get complex solutions. So we don't need to worry about x squared plus 4. However, this one is another difference of squares. That's x plus 2 times x minus 2. So this one splits into x plus 2 times x minus 2. And if you were to solve each of these sets of parentheses by setting them equal to 0, what would the values of x be? 2 and negative 2. Negative 2 for that one, positive 2 for that one. So x equals 2, x equals negative 2. Or if you want to, you could write x equals positive and negative 2. This is the long way by using factoring. So that means that on that function, if you were to graph it, the real solutions where it crosses the x-axis, it would cross the x-axis at negative 2 and positive 2, if you were to graph it. Now, there's a quicker way of solving this, and the quicker way would just be to say the 4th root of 16. So if you take the 4th root of 16, that would be x equal to the 4th root of 16. What number multiplied by itself 4 times equals 16? 2. 2 times 2 times 2 times 2 is 16. Also, negative 2. Because when you have an even, by the way, this is what's called an index, this 4. Listen up. I will be using this terminology. This is what's known as an index. And if you have an index that is even, when you are rooting something, an even index value for your root, you can have positive and negative answers. Because when you multiply 2 negative 2's together, you get positive 4. When you multiply another 2 negative 2's together, you get another positive 4. If you multiply 4 and 4 together, you get 16. So positive 2 works, negative 2 works. So that means the 4th root of 16 is positive and negative 2. So instead of factoring and solving using factoring, you can just use the 4th root if you know what to use. And I'm going to give you a list of roots and exponents as well at some point. So let's look at A and B down here. I want you to answer A and B real quick. You do not have to use factoring. So we're looking for real 4th roots of 81, and we're looking for real cube roots of 64. Take a minute or two on those. Let's see. We're all here today. What's up? For this unit? No. We'll go through a few lessons and turn some assignments in, but we're not going to do a test with this one before the end of the term. All right, so for A, what number or numbers would multiply by itself or themselves to equal 81? 4 times. 3, yeah, positive and negative. So basically what we're saying is that the 4th root of 81 equals positive 3 and negative 3. 3 times 3 times 3 times 3 is 81. Negative 3 times negative 3 times negative 3 times negative 3 is 81. If your index is even, you'll have positive and negative answers for the answer, unless what's underneath the radical symbol is negative, in which case it doesn't work. So if you try to root a negative with an even index, you can't do it because nothing is going to multiply by itself an even amount of times to be a negative number. Now the opposite can work, but this one is positive anyway. So what number multiplies by itself 3 times to equal 64? 4. Just 4 or 4 and negative 4? Just 4, yeah. Because odd index values are going to be either positive or negative, which also means you can root an odd index. If that was negative 64 under here, this would be negative 4 here. So even indexes get 2 answers as long as your radicand, the number under the radical symbol, is positive. Odd indexes have a single answer depending on what the radicand is under the square, or under, not square root, but under the radical symbol. All right, any questions here before we continue? This is probably stuff that some of you have actually done before, so hopefully, you know, to some degree, this might be some review. However, once we get to the next page, this stuff might look a little bit new because I don't know if you've ever seen anything with an exponent that is a fraction. By the way, fractions are what are called rational numbers. Any number that you can write as a fraction is a rational number. So when we talk about rational exponents, basically what we're saying is exponents that have fractions. So this is asking you, what is the meaning of the exponent in the expression 16 to the 1/4 power? All right. So it says to extend the properties of integer exponents to rational exponents. So first thing I want to do is just say that 16 to the 1/4 power, go and write this down, 16 to the power of 1/4 is equal to now 16, if we were to, let's just factor 16 real quick. If we're going to go over here, let's say factor, like prime factorization of 16. What times what equals 16? Give me 2 numbers that multiply to equal 16. Doesn't matter which ones. 4 and 4, great. 4 times 4 is equal to 16. Give me 2 numbers that multiply to equal 4. Don't use 1. 2 and 2, okay. Which means that this one is also 2 times 2. So the prime factorization of 16, you remember doing this in grade school? Prime factorization? Basically break it down to do its simplest factors. So 2 times 2 times 2 times 2. That is the prime factorization of 16, which is 2 multiplied by itself 4 times, which is 2 to the power of 4, right? So we can replace 16 with 2 to the 4th power. So I'm going to do that real quick. 2 to the power of 4 to the power of 1/4. Take a look. Eyes up here, guys. You need to understand how this works. So 16 is 2 to the 4th power because the prime factorization of 16 gets 2 4s. So we're replacing 16 with 2 to the 4th power. Those are the same thing. And we still have the 1 multiplied to 1/4 power over here. Now, if you think back to Algebra 1, and I can't remember if we've done this year or not. Let's go off to the side here. Let's say x squared to the power of 6. We're basically looking at the same thing on the left over here and the right over here, except one of our exponents on the left is a fraction. Both of our exponents on the right are just integers. Does anybody remember what to do with exponents if you take a power to a power? You multiply them. Yeah. So this would equal x to the power of 12. If you take a power to a power, you multiply the exponent. 2 times 6 is 12. What about over here? What's 4 times 1/4? 1. 2 to the first power is just 2. So what we're saying here is that 16 to the 1/4 power is equal to 2. Now go back to the previous page for a second. We just said a minute ago that the 4th root of 16 is 2 and -2. And now we're saying that 16 to the 1/4 is the same answer, it's 2. Keep that in mind. That will come in handy. So, and I think on this one, doesn't say it specifically, but it says, yeah, we're not going with the negatives right now, so we'll talk about this in a couple minutes though. All right, let's try this next one. Write 27 to the 2/3 power as a radical. Before we do that though, we can say, so 16 to the 1/4 is equal to the 4th root of 16, which is equal to 2. Basically, we just showed that. Because on the previous page, we had the 4th root of 16. Here we said 16 to the 1/4. They both ended up having an answer of 2. So we're basically saying that those two things are the same. 4th root of 16 and 16 to the 1/4, same deal. So we try part B. We try part B real quick. Let's see what happens with that one. Write 27 to the 2/3 as a radical, meaning use the radical symbol in your answer. So 27 to the 2/3. Is there any way to rewrite 27 using an exponent instead of just 27? So if you were to factor 27, somebody give me two numbers that multiply to equal 27. 3 and 9. All right, so 3 times 9. 3 is a prime number, but 9's not. What multiplies to equal 9? Should be 3 times 3. So 27 is equal to 3 times 3 times 3, which is 3 to the power of 3. So we can rewrite 27 to the 2/3 power as 3 cubed to the 2/3 power. Now, would you agree that 2/3, listen up, because you're going to be having to deal with a lot of like little switching around and moving things around with today's lesson. So would you agree with me that 2/3 is equal to 2 times 1/3? Like if we were to just take this and go over here for a second and say, that's the same thing as 2 times 1/3. Because the whole number times a fraction is just the whole number times the numerator. 2 times 1 is 2. 2 times 1/3 is 2/3. Which means this could be rewritten as 3 to the power of 3 times 2 to the 1/3 power. There's a lot of little things that you can use to manipulate exponential rational numbers to kind of make it how you want it. So if we are rewriting this as a radical, think about this for a second. if 16 to the 1/4 power was equal to the 4th root of 16, 3 cubed squared to the 1/3. What do you think 1/3 power means? What's that? So 1/4 was 4th root, so 1/3 is going to be cube root, yeah. So we could rewrite this as the cube root of 3 to the 3rd power squared. Now, cube rooting something and cubing something are equivalent, right? Not equivalent, but sorry, inverse operations. Like squaring and square rooting are inverse operations. A cube and a cube root are also inverse operations, which means that if 3 cubed and the cube root of 3, those will cancel each other out, including the radical symbol, which leaves us with 3 squared, which equals 9. Do what now? Oh, like from here?
Yeah.
Yes. You could multiply 3 times 1/3 and cancel those. That is perfectly fine. The only reason why I wrote it like this is because it told us to write it as a radical.
Oh.
If I was doing this without telling us to write it as a radical, I would absolutely go from here to the answer, because that is quicker. I'm just showing you this because you need to know how these interact in terms of like transitioning between rational exponents and radicals. Yeah. Okay. Let's try A real quick. What does 25 to the 1/2 mean? Or the square root of 25, right? Yeah. This would be, yeah, you could write it as 5 squared to the 1/2, but basically what this means is the square root of 25, which could be written as 5 squared to the 1/2. Either way, what's the square root of 25? 5. Here, 2 times 1/2 is 1, 5 to the 1st power is 5. Either way, the answer is 5. Over here, we're looking at 32 to the 2/5 power, which would be equal to 32 squared times 1/5, or 32, if you factor this out into prime factorization, is 2 to the power of 5. To the 2/5. Now, you don't even need to separate this out necessarily. You could just say 5 times 2/5. What is 5 times 2/5? It would be multiply the 5 and the 2. What do you get? 10. 10/5. What's 10 divided by 5? 2. So that would be 2 squared. So the answer is 4. Now, in terms of a radical, this would equal the 5th root of 32 squared. So if you're to write, just straight up write that as a radical, you'd get this, 5th root of 32 squared. It all ends up working out the same way though. So there's a lot of ways to work your way through this. Now, here's the thing. We don't need to know what 32 squared is in order to solve this. That's one of the nice things about dealing with rational exponents, is that if you can convert large values like 32 squared, which is more than 900, I don't know exactly what it is, but it's more than 900, you don't ever have to know that. You just use rational exponents and cancel things out and just pare it all down to 4 without actually knowing what 32 squared is. So basically means you don't have to use a calculator to deal with this stuff. All right, any questions here before we turn the page? I like this stuff because this is like classic algebra type stuff, and I enjoy that. So, questions at all? before we move on? Good? Cool. Turn the page. So our first rule, here you go. This is our first rule that we're actually writing out. So this says, in general, if the nth root of c is a real number, the nth root of c is equal to c to the 1 over n, which would be the same thing as, listen up, that'd be the same thing as taking like, let's say the 6th root of 75, okay? 6th root of 75 would equal 75 to the 1/6 power. That's our example right there. We did that on the previous page. So now you have a rule for it though. So you can just switch between them whenever you want to, or if it tells you to, or if it's convenient to do that, however that works out. So next here, furthermore, if m, we're introducing another variable here, m is an integer, positive or negative whole number, then c to the mn power is equal to c to the 1 over m to the 1 over n to the m, which is equal to the nth root of c to the power of m. What that means is, let's say you've got 6 to the 3/2 power. This would be equal to, according to this little progression, would be 6 to the 1/2 cubed, which would be equal to the square root of 6 cubed. Also, you could also write it like this. You could have the square root. I don't even know why I put a 2 there. You don't need a 2 if it's a square root, but you can if you want to. You could take the square root of 6 cubed. This is the same problem. And write it as 6 cubed to the 1/2, which is equal to 6 to the 2/3. Basically, there are a lot of different ways to write the exact same thing is what we're being told here. So we've got 1, 2, 3, 4, 5 different ways. Because the first and the last are the same. There's 6 things here, but 5 of them are different. Just slightly. But there's a lot of different ways to write the exact same thing. Depending on what's useful in a problem, you might need to do any one of these 5 things. But knowing that you can switch between all 5 of these whenever you want to, that could become a really useful thing as we're working through these types of problems. So let's go ahead and take a look here. Evaluate the expressions. Evaluate just means solve, get an answer, get a number. So if we look at 32 to the 3/5 power, let's look at that one. There we go, 32 to the 3/5 power. Now, generally speaking, if I can write a number in its prime factorization with an exponent, that's how I prefer to do that. Like 32, I know is 2 to the power of 5. So rewriting 32 as 2 to the 5th power, for me, that's going to make this problem a lot quicker. I don't really care what the 3/5 power looks like as a radical. I just want to get an answer. So 2 to the power of 5 raised to the 3/5 power. 5 times 3/5 is 15/5. 15 divided by 5 is 3, so that's 2 cubed, which is 8. The answer is 8. 32 to the 3/5 power equals 8. And because I changed 32 into 2 to the 5th power, that made it a lot easier. Because if we just multiply these, 5 times 3 is 15. 15 divided by 5 is 3. 2 cubed is 2 times 2 times 2. The answer is 8. So problems like this, knowing how to work with rational exponents or converting nth root values into rational exponents can really help you out, especially if you don't have a calculator, because we didn't need a calculator for that. Let's try the next one, 27 to the negative 2/3 power. 27 is equal to 3 cubed. So that would be 3 cubed to the negative 2/3. By the way, the 3 and the 3's are going to cancel out. So that would be 3 to the negative 2 power. Now, quick question for everybody here. What does a negative exponent make? Okay, a positive what? A negative exponent doesn't make a negative number. You're correct about that. What does it create, though? Anybody remember? All right, let's go over here. Right, 3 to the 4th power on the left side. 3 to the 4th power equals 81. Because it's 3 times 3 times 3 times 3. 3 cubed is equal to 27, which is equal to the previous number divided by 3. So that equals 81 divided by 3. 3 squared equals 9, which equals the previous answer of 27 divided by 3. So if we're talking about our power here, the base value is 3 every single time. If you reduce an exponent, you're dividing by 3. If you add an exponent, you're multiplying by 3, right? Adding an exponent multiplies by 3. Taking away an exponent should then do the opposite, which is dividing by 3. So that means that 3 to the 1st power is equal to 3, which is the previous answer divided by 3. 3 to the 0 power. The previous answer was 3. Divide that by 3, what do you get? What's 3 divided by 3? 1. Which is why in Algebra 1, you learned that anything to the 0 power equals 1. And that's because if you have something to the 0 power, you're taking the previous exponent value and you're dividing it by the base value. So 3 divided by 3 is 1. So if you have 3 to the negative 1 power, that's equal to the previous answer of 1 divided by the base value of 3, which equals 1/3. So a negative exponent creates a fraction. If you have 3 to the negative 2, that's the previous answer 1/3 divided by the base value of 3. 1/3 divided by 3 is the same thing as 1 over 3 squared, which is 1/9. So basically your denominators are now the ones that essentially get the exponent, right? So over here, the answer is 1/9. So 27 to the negative 2/3 power is equal to 1/9. No calculators needed. Now the next one, 50 to the 3/4 power. This one's not going to be so easy. And the reason for that is 50 does not turn into prime factorization to an exponent. Like the prime factorization of 50 would be 5, 5, and 2. So this one is definitely not so straightforward. So what do you think we could do to write this one? Let's use this rule right here. This would end up being what? Write it as a radical. Somebody tell me what this looks like as a radical for this one. Well, here's our, if you split it apart with exponents, it looks like that. So as a radical, what would this look like? What's our index root value here? 4. So it's a fourth root of, it's the fourth root of 50 cubed. Now, if you want to, you could type it like that in your calculator. However, it's probably just easier to use the exponent button on your calculator and type in 50 to the 3/4 power. So what is that approximately? Give me 2 decimal places. 18.8. Yeah. And the next number would be 0 after that. So if you go 2 decimal places, you're looking at about 18.80. If it's not a whole number, it's not going to factor very nicely. And if that's the case, just use your calculator. That's fine. You're always welcome to use your calculator, but you don't always have to. All right. Any questions so far? And by the way that I wrote these first two out, that's just a preference of mine. These could have been written as the fifth root of 32 cubed. This could have been written as the cube root of 27 to the negative 2 power. You could write them as radicals if you want to, but I prefer to keep the exponents in rational form because I find that to be a little bit quicker for me. All right, let's try the next one. Anybody ever heard of like F ratings of tornadoes, like an F4 category tornado? That's what we're talking about here. So there's a formula for it. It says the F stands for Fujita, by the way. The Fujita scale rating F of a tornado is represented by F is equal to the cube root of W divided by 14.1 squared minus 2, where W is the estimated wind speed of the tornado in miles per hour. What is the Fujita scale rating for this tornado? If you have 100 miles an hour wind speed, the only thing we have to do here is type in 100, not type in, but write in 100 for W. Just substitute 100 for W. So you're going to say F equals the cube root of, here we go, 100 divided by 14.1 squared, and then minus 2. Now we could write this as a rational exponent. So let's go and do that real quick. That's going to be, let's see, I'm going to use a bracket here. And then we're going to have 100 divided by 14.1 squared. And then if we turn cube root into an exponent, what's the exponent? If you write cube root as an exponent, what's the exponent? What does that turn into as an exponent over here? 1/3, all right? So 1/3 and then minus 2. Double check something here real quick. 14.1, see if that's a nice number. It's not. 100 divided by 14.1 is not a nice number. So last thing I'm going to do real quick, just to condense this a little bit more, is write this as 100 divided by 14.1 to the, if we combine those two exponents, what's our new exponent? 2/3, yeah, multiply the exponents, power to a power, 2 times 1/3 is 2/3, and then minus 2. So on your calculator, it might be easiest to write it like this, as opposed to starting here. So here we go. We've got ourselves parentheses. So open up parentheses on your calculator. And then fraction. 100 over 14.1. Close it on up. Exponent. Another fraction. 2/3 this time. And then all the way back down, minus 2. And if we type that in, that gives us about 1.69. So approximately 1.69, which would be an F1. They are, I think it's rated on integer as opposed to approximations. And so you would round that 1.69 up to 2. Until you get to 2, you don't call it an F2, basically. So anything between 1 and 2 is an F1. So this would be considered an F1 hurricane. So F1 rating. If it got to 2, then it would be considered an F2. All right. By the way, you could have just typed that into your calculator. That's fine too. That does work. It didn't? Oh, well, yeah, let's try it out then. So we're going with cube root. By the way, if you want to get an nth root value, click on math. and then go to option 5, where it's the x on the outside of the radical. You can type in any index value you want. So this is an index value 3 because it's a cube root. And then inside, we're going to do parentheses and then a fraction. Type in 100 over 14.1. Close that up. Oops, delete. Go to the right, close it up. Then square it. Now we need to go outside of the radical. So go to the right once more. And then minus 2. So it should look like that. And that should give us about, there it is, 1.69. So these calculators do a lot of cool stuff. You can type it just as the regular radical. You can type it as a rational exponent. Same thing either way, but knowing how to convert between the two is kind of the idea of today's lesson. Questions on that one? Before we keep going. Cool, flip it over. Have a look at the next one. So, what is the value of each expression round to the nearest hundredth if necessary? So this one here, that is 16 to the 3/4 power. Now, you could use your calculator for this and just type it in, that's fine. That would give you an answer, but 16 can be written as an exponent of 2. So I'm going to do this one by hand. So let's follow along with this. So we're going to go negative. 16 is equal to 2 to the 4th power. And then that would be to the 3/4 power. Which ends up, I think this ends up being probably a little bit quicker than using a calculator anyway, because those cancel out. 2 cubed is 8, so the answer is negative 8. Now, if you type in negative and then parentheses 16 to the 3/4 power, it should be negative 8 as well. The next one, on the other hand, that one needs a calculator. And you can just type it in the way it is if you want to, or if you want to change it to a rational exponent. Somebody tell me, what does this one look like as a rational exponent? 3.5 to the what? The rule for it is on the top of the previous page right here. So right now we're looking at something that looks like this. And we're converting it to this. So the exponent on the inside of the parentheses will be the numerator of your exponent. The index value is the denominator of the exponent. So 3/5 to what power? What's our fraction exponent here? 4/5. Good. You can just type in 3.5 to the 4/5 power. You don't actually need the parentheses either. You can just do 3.5 to the power of 4/5, which gives us an answer of approximately 2.72. So it's about 2.72 for this one. There we go. All right. Now that we're kind of finished with like getting answers and just being able to use our calculators all the time, these next ones introduce a combination of numbers and variables with exponents. So this is where knowing the rules for how to convert things from radical to exponential form are going to come in pretty handy. So simplify each expression, assume all variables are positive. So assuming all the variables are positive just means that we can get positive answers for everything here. We are not solving for m. I want to make that clear. We're not solving anything right now. This is not an equation. This is an expression. So we're just simplifying it. So let's rewrite this in exponential form. So this is going to be, first of all, 32 can be simplified to 2 to the power of 5. So this would be 2 to the 5th power times m to the 15th power. And then what's our rational exponent going to be? If it's an index of 5, what's our rational exponent? 1/5. Okay. So 2 to the 5th times 1/5. 5 times 1/5 is 1. That's just 2. 2 to the first power is 2. 15 times 1/5. What's 15 times 1/5? 3. That'd be 15/5. 15 divided by 5 is 3. So the answer is 2m cubed. That's how that's simplified. So we're using our rational exponent rules in order to simplify these down. Do the next one on your own. That one doesn't have any numbers with it, just variables and exponents. So give that next one a try. How we do on B? Take a look. By the way, you can also take this exponent because if you multiply this by 1/4, that's the same as dividing it by 4. 20 divided by 4 is 5. 8 divided by 4 is 2. But you could write it as a rational exponent. That'd be x to the 20th, y to the 8th, to the power of 1/4. 1/4 times 20 is 5. 1/4 times 8 is 2. So we get x to the 5th, y squared. Cool. Try 4A and B at the bottom. Take a moment on those. Same types of questions for those at the bottom. I'll work on them as well, but I won't show them until we have a chance to check out our answers. All right, there's A, there's B. So for A, -8 is the same thing as -2 cubed. So I wrote -2 cubed times A cubed times B to the 9th to the 1/3 power. 1/3 times 3 is 1. -2 to the first power is -2. 1/3 times 3 is 1. A to the first power is A. 9 times 1/3 is 3. B cubed. So -2A B cubed for A. For B, 256 is the same thing as 4 to the power 4. So I wrote 4 to the 4th power, x to the 12th, y to the 24th, multiplied each of the exponents by 1/4, and that simplified to equal 4x cubed, y to the 6th. Yeah, and go straight to here. Yeah, if you know how to get from straight to the problem to the answer without writing anything in between, that's fine. I'm just still reinforcing how these things work, so I'm writing in the middle bits, but yeah, you got it, great. Any questions on A or B down here before we take a look at the next page? How are we doing so far? Not too bad, right? Cool. All right, to the page. We'll probably finish off with these A's and B's here, and then we'll finish the rest of the assignment or lesson tomorrow. So the only reason why there are graphs for the main examples here is just to give you a visual. You will not necessarily have to make graphs in order to answer these questions. This is more of just kind of showing you, you can use your graph to graph the functions to kind of give yourself a visual approach if you need to. So if you are solving the equation, 2x to the fifth equals 64, what you can do is break this into two different functions. You could write y equals 64, and you can write y equals 2x to the fifth power. Basically, take each side of the equation and write them as a separate function. Y equals 64 is a horizontal line here. 2x to the power of 5 is this function here. And you can see that they intersect at this point right here, which on this graph looks to be about maybe 2.1 for the value of x. And so that's what we're solving for here, by the way. We're solving for x. So this particular problem, when you're solving an equation using nth roots to solve an equation, it's very much like solving a regular equation. So the first thing you want to do is isolate the variable, but in this case, isolating the variable with its exponent. So how do we do that? How do you get x to the fifth by itself? We got 2x to the fifth. We want x to the fifth by itself. What do we do? Yeah, divide by 2. Undo the multiplication of 2 by dividing both sides by 2. So that'll give us x to the fifth power equals what? 32. So we're looking at the fifth root of 32. So x is equal to the fifth root of 32, or 32 to the 1/5 power, or 2 to the fifth power to the 1/5. However you want to write that out, because we've got about 4 different ways that we could write that. I would probably go with this, because then I know the answer is just 2. Or if you know what the fifth root of 32 is anyway, the answer is 2. So x equals 2. All right. Try the next one on your own then. I'm going to ask you something in particular once you solve this next one. What's our answer here? 5, okay. Now, look at the graph. Plus or minus 5, yeah. It's not just 5. Here's where things get a little bit different, because we haven't really had to deal with the plus minus for most of this lesson today. So I'm going to back it up just a little bit. If you are dealing with expressions, stuff like this, an expression does not have a variable, meaning it will tell you whether or not the value is positive or negative ahead of time. Okay, if there's no equal sign, if there's no variable, and you're just simplifying, it'll tell you whether or not you're working with a positive or a negative number. That's going to be true of anything with an expression. All this stuff here with expressions, these were all positive values, which was fine. There wasn't an issue with that. However, as soon as we get to variables, variables are unknown. Expressions are known, variables are unknown. So if you have a variable and it's an unknown, if your index value is odd, we talked about this at the beginning of the lesson, if your index value is odd, there will be only one answer. So write this off to the side. Odd index, one solution. even index, possibly two solutions. And I say possibly because if it's 0, there's only one answer, but most of the time there will be two answers if you have an even index. All right. Go and pack up your stuff. We will finish these notes tomorrow. There's not much left to go, and then you'll have the remainder of class tomorrow to work on the assignment. So